So today I want to talk about a paper I came across recently, and I found the idea interesting, so I wanted to share it with you. The paper is called Considering Time in LCA, Dynamic LCA and its Application to Global Warming Impact Assessment. It was published in 2010 and has already, I think, 700 citations today. Before talking about why we should consider time in LCA, I should probably mention why traditional LCA lacks some coherence, I would say. First, a quick introduction to what LCA is. So it means life cycle assessment. The idea is to assess the environmental impact of products and services. It consists of 4 phases, although the fourth one is interpretation phase, and it is done at the end of each phase. So I wouldn't say it's really a phase, it's more something you should do, because if you don't interpret what you do, then what's the point of doing it? So it has really 3 phases, the goal and scope, the inventory, and the impact assessment. The first phase, goal and scope, aim to define what product you want to assess and the boundaries from which you will compute your LCA. So for instance, let's say we want to assess the impact of a phone. The first step would consist in deciding whether we take into account transport, design of the phone, the production. Probably a good idea to take into account the production, but transportation or design is probably negligible compared to production. And so you could neglect that part. And by the end of the goal and scope, you would have what's called a reference flow. So a quantity of products you will have to assess the impact of. The second phase consists into taking your reference flow, so here a phone, and to determine all the gases that are emitted during its life cycle. So during its production, its use phase, its transportation, and so on and so forth. During the inventory, you start with this product and you list all processes that are needed to produce this one. And in those processes, there is 2 matrices involved, the technosphere and the biosphere. And in the biosphere are listed all the gases that are emitted during those processes. So by the end of the inventory phase, you should have a list of gases that are emitted, here methane, nitrous oxide, carbon dioxide, and the amount of those gases that were emitted. And the last but not least phase is the impact assessment. And here the idea would be to take those gases and gather them into one value. Here for this, for the gases, it would be the CO2 equivalent. Keep in mind that I only talked about global warming here. There are other impacts, but for this study, we're only interested in global warming. So the third phase would consist into aggregating all those gases into one value. And the question is, how do you do that? For those who were present in the last month, you probably have seen this slide before, not exactly this one, but the idea. So to understand how CO2 equivalent works, we need to understand how global warming works. And the idea of global warming is that Earth has a temperature, and its temperature is determined by the amount of energy it receives. So Earth receives energy from the sun's radiation, and it has to emit as much energy as it received by the sun to be in a balanced state. So it emits also energy. This emitted energy is proportional to its temperature. So it has to increase its temperature to be able to radiate as much energy as it receives by the sun. The problem is this emitted energy doesn't go into space, it goes into the atmosphere. And the atmosphere, while it is mostly transparent to sun's radiation, it absorbs Earth radiation, and by absorbing it, it increases its temperature. And because the atmosphere has a temperature that increases, it also emits energy. So Earth not only receives energy from the sun, but also from the atmosphere that Earth heated up beforehand. And the idea is that the sun's radiation is more or less stable, but the more we emit greenhouse gases, the more the atmosphere becomes opaque to Earth's radiation, and thus the more its temperature increases, and the more radiation comes to Earth. And because Earth receives more radiation that it emitted, it has to increase its temperature to be at a balanced state again. The amount of energy received by the Earth, the difference between its stable state and the amount of energy it received is called radiative forcing. And here are some examples of radiative forcing of three gases, so carbon dioxide, methane, and difluoroethane. Those are the resulting of emitting 1 kilogram of each gas over time. And as you can see, the impact of the radiative forcing caused by those gases decreases through time. This is only because, for instance, for carbon dioxide is absorbed by some plants in the atmosphere. So when time goes, the concentration of carbon dioxide decreases, and thus its impact decreases as well. Be careful, carbon dioxide and methane are scaled up, because if I didn't do that, carbon dioxide would be here. So this red curve here is much more important than it looks now. So now, based on this, how do we compute the CO2 equivalent? We do that by integrating. So we could have used the value at time 0, but as you can see, it is not a really good value, because by 10 years, you divide it by 2 the impact of methane, for instance. So a better idea would be to integrate the value over a period of time. Again, we could integrate over an infinite period of time. Okay, that looks logical to do. The problem is the model used for the CO2 radiative forcing has a constant in it. So if you integrate over an infinite period of time, you get an infinite value, and then you can't do anything. So we integrate over, let's say, predetermined period of time. Here I put 100 years, which is the standard value used by the GWP, but there are other values we'll talk about later. So to compute the global warming potential, which is called CO2 equivalent in French, you integrate, let's say for methane, you integrate the radiative forcing of methane, and you divide it by the radiative forcing of carbon dioxide. The reason is, if we do not divide it, we get a value with a unit that is not very meaningful for many people. And the idea is to divide it by a reference value, which is carbon dioxide, so that people can compare results between the methane and carbon dioxide here. So if you do this computation, you find around 22 kilograms. It can change. We will talk about that later as well. And if you do the same thing for difluoroethane, you find 120. So again, because this curve was diminished, so it looks like it is negligible compared to CO2, but it is not. Here are some results of GWP, so global warming potential of 3 gases, the same two as before, and nitrous oxide, over different period of time, so 20 years, 100 years, and 500 years. Those are very classical, although 100 years is very often used. And here you can see that, for instance, for methane, by using 20 years instead of 100 years, you almost multiply it by 3. And if I show you the sector in which those gases are the most emitted, so for CO2, it's energy production, and for methane and nitrous oxide, it is livestock. You can see that by computing my global warming potential over 20 years instead of 100 years, you increase a lot the impact of methane, and you decrease very slightly the impact of nitrous oxide, while keeping CO2 unchanged. The reason is because it is the reference, so always divided by itself, so it gives always 1. And consequently, you increase the impact of livestock, and by contrast, you decrease the impact of energy consumption, energy production, sorry, just by changing the time period you're computing your global warming potential value based on. And on the opposite, if you increase your time window to 500 years, then you decrease a lot the impact of methane, and as well the impact of nitrous oxide. So here you would drastically reduce the impact of livestock, and by contrast, increase the impact of energy production. So what's the problem in the end with classical LCA? Let's say we want to compute the life cycle assessment of television. It's just a toy example, so uh, don't overthink the hypothesis I took here. Let's say it emits two kilograms of gases 2 times in its life. The first one being at its production, and the second one being 80 years later when it is recycled. Then the first emission here is taken at between t equals 0 and t equals 100 years, if we get a GWP of 100 years. Okay, so by taking global warming potential with the time window of 100 years, we are computing the impact of the emitted gas production from t0 t equals 0 and t equals 100. But for the emission of the recycling, it is taken between t equals 80 and t equals 180. And then we're comparing two things that are very different, because here you can see this emission as it still impacts the atmosphere here, but we do not take it into account because we cut our integral to 100 years. So we are taking into account a dark green area from the second emission, but not the light orange area from the first emission. So it's not very coherent. And the idea would be to do what's called a dynamic life cycle assessment to tackle this issue. And when you do a dynamic life cycle assessment, pretty much like you would do in JWP, you choose a time window from which you will compute your LCA. And the idea is, instead of pre-computing the CO2 equivalent like we did before, 22 for methane and 120 for I can't remember the other gas, but for the second gas, here you compute the radiative forcing curve of all gases, and then you integrate over your period of time. So first, to compute your radiative forcing, you do a convolution between your timing of emissions. So here we had two emissions, one at production at t equals 0, and the second one at t equals 80. And you convolute it with the radiative forcing due to 1 kilogram of that gas. And by convoluting them, we get this curve, which is here the radiative forcing of the first emission, and here the second one, and the curve in red is the sum of them both. And if we were to compute the impact based on CO2 equivalent as it is done usually, the result would be the area in green here. And as you can see, you're taking, again, into account something here that is not taken into account here. It was, I think, clear before. It is even clearer here. It is not coherent to either you don't take this, either you take this, but getting one and not the other is I think, a mistake. So here, the idea of dynamic life cycle assessment would be to choose a time window, let's say 100 years, and the impacts after 100 years are not taken into account. So here, our result would be the area in green here. Obviously, we can't really compute this area as is, because, for instance, let's say you have a car from which you want to compute the life cycle assessment. The car will emit gas every time you use it. So we have to choose short period of time over which we are computing the mean emissions. So let's say you take the emission of your car over a day, and you compute life cycle assessment over that day, but not over every second or every minute or every year or anything. So here we discretize time, and instead of computing the real value of this curve, we use a staircase curve, and finally the last value of the GWP, which is here, is the area under this curve. So the area in green here. So this is the basic idea of dynamic life cycle assessment. And in their paper, they chose a use case, which is corn ethanol versus gasoline. So those are two liquids used to power engine. And they computed the GHG emissions per unit energy over time. And as you can see, biofuel has a big peak of emissions at t equals 0. And then it is lower than gasoline and even becomes lower and lower over time. The reason of this first peak is that we assume it is a first generation biofuel. So in order to be able to plant your plants you will use in your biofuel, you have to get rid of existing plants. Those plants captured CO2, and by burning them or letting them rotten, you emit either CO2 or methane, and this is what's taken here into account. But then, as you're using your lands to produce biofuel, you don't have to get rid of plants because you already did it, and you use the plants you planted the year before. And here, the impact decreases, but is not null because you're taking place of other vegetation that could capture CO2. So you're still not really emitting CO2, but you're not capturing CO2 that you could capture. So by doing a traditional LCA, we will get this result. This curve shows the relative impact of gasoline and ethanol. So when you're on the top, it means that gasoline is has less impact on the environment than ethanol. And when you're on the lower end of this curve, it means that ethanol has less impact. And as you can see, if we compute an LCA over 30 years, then gasoline is better because of the first big emission. But then, as time goes by, ethanol becomes better and better. If we were to compute a dynamic LCA, the results change a bit. As you can see, the impact over the first 30 years are way greater, and even after that, the impact of ethanol was, I would say, is a bit lower now than it was before. And the reason is that most of the emissions of ethanol are occurring at T equals 0. So when you compute the CO2 equivalent, during 100 years, those gases are taken into account, whether it is in traditional LCA or in dynamic. But when you go into dynamic in traditional LCA with gasoline, because it is emitting every time, I will come back to explain that. All those emissions are taken into account for traditional LCA, but in dynamic LCA, this emission has less impact than this one because we're cutting the integral at 100 years. So those emissions are less impactful, but because they are occurring later, they're less impactful. And this one, because it is occurring earlier, it has a much more impact in dynamic LCA. So that's why we get this kind of result, and the results, although it doesn't change the conclusion of the that ethanol is better when computed over 100 years, we can see that its impact is much more important than it was before we used dynamic LCA. Although dynamic LCA helps us to compute better or more coherent, I should say, LCA, it has, I think, still a problem. And the problem is that the impact of gases in the atmosphere is not stationary. So here, this is the formula that occurs in the atmosphere with the methane and hydrogen radical. Sorry. So when methane is emitted, it reacts with hydroxyl radical and this is one of the reasons why methane has a short-lived period in the atmosphere. The problem is that this equation can only be true if we have hydroxyl radical in the atmosphere, and the amount of hydroxyl radical in the atmosphere changes over time. So even if today we are able to reduce the amount of methane in the atmosphere, maybe tomorrow, if we have less hydroxyl radical, the atmosphere will be less able to deal with the quantity of methane. And also, it emits H2O, so water, and water is GHGs, or greenhouse gases, although this one is negligible because there are too much, anyway, there are too much water in the atmosphere, so the water we are emitted as humans is negligible compared to that. But this molecule here, we create a chain reaction because it's not stable. And this chain reaction will, amongst other, create ozone, and ozone is also greenhouse gases. So by reducing the amount of methane in the atmosphere, we are increasing the amount of ozone. And I don't think that's something that is taken into account in the decreasing exponential that represent the radiative forcing of methane over time. So to conclude, traditional LCA works fine for short-lived products. Do not throw it in the bin. It works fine for short-lived because compared to 100 years, you're only you're only taking into account a short bit of exceeding a short bit that is exceeding your time window. So it's not a big deal. So to conclude, the error is very short. But for long-lived products, it lacks coherence because you're taking into account some things for one emission and not other things from other emissions that are occurring in the same time. One consequence of using dynamic LCA is that early emissions are more impactful. We saw it with the gasoline and ethanol. And well, this is something that well, may be a problem, I would say. It is logical because, well, you want to delay as much as possible the amount of gas you're putting. If you put all the gas will be emitted in 100 years right now, it is probably more a problem than emitting it over time. But anyway, it is something to be aware of. When you use dynamic LCA, your emissions now are more impactful. And let's say you have you're computing an LCA over 100 years, and you have a car that will be used 101 years, then the recycling of that car will not be taken into account because it exceeds the time window of your LCA. And finally, to compute dynamic life cycle assessment, you're required to know the timing at which gases are emitted. So for instance, if you have a phone, you need to know when this phone will be recycled and everything. And this is currently what I'm working on. So I'm working on models that would be able to predict at which time those gases are emitted for any product. If you have any question.